Okay, so we're gonna. And now in the it kind of gets harder now. So that was kind of the easier stuff. The course kind of gets harder. We really have to keep track of what we're talking about. So you may have to really take the time to stay up on your studying, especially with our our 4-day weekends, 5-day weekends from the class. Don't let everything fall out of your brain after class. Okay, sampling distributions. Okay, so we have this data. Heights of 5 basketball players. I guess this is in inches. Heights in inches. Okay? Player A, B, C, D, E. So what we're going to do is we're going to take samples of size 2. And when we take samples of size 2 out of these 5 players, we get all, these are all the possible samples. 10 possible samples when you have a group of 5. So 10 samples of size 2 when you have a original data set of 5 items. Okay, and so what they've done here is they've taken each of those samples and they found the mean. They found the mean height for each sample. So remember this notation means sample mean, or the sample average. Okay, so if your sample was player B and player C, then the mean for that particular sample was 78.5. Right there. That's showing it right there. So this is all possible samples of size 2. Does that make sense so far? So what happens is now if you look at these means, we have these 10 means. Those 10 means in of themselves are a data set. So now we have a data set of 10 values. And what's the variable? The variable is sample means. Okay, so our original data set was just these 5 heights. But now we have a data set of 10 sample means. So new data set. So we get this new variable, and the new variable is the sample means for samples of size 2. So this is a really important concept. We're going to talk a lot about it, and you have to see what's going on. So original data was 5 heights. What was the value of the variable? Height. A basketball player's height. That was the value of the variable. Now we take all the samples of size 2 and we find the means of each sample size 2. That's a new data set. And what's the value of that variable? Sample means, right? The sample means is the new variable when you're looking at this data set. Okay? And so that's what we're going to be dealing with here coming up next, is forming a new set of data out of the means of all your samples that you take. Okay, so for the here's a summary for variable x and equally sized samples. The mean of a sample is itself a variable. X bar is itself a variable. Its value varies from sample to sample. Take one sample, you get a certain mean. Take another sample, the mean will be different, right? Thus, we can investigate the distribution of the variable x bar. New variable x bar. Does it make sense? Okay, so then the distribution of that variable x bar is called the sampling distribution of the sample mean. The sampling distribution of the sample mean. Okay, anybody have a question? So you kind of, so you have to have this is all kind of, you really have to have this, an imagination of this kind of, because it's like multi-layered now, right? We've got the variable, it has a distribution. Then we take all these samples, take 6 samples of size 3, get a sample of size 3, get a sample of size 3, get a sample of size 3, and then each one of those has a mean. And now we're doing a distribution of those means. You have to, so there's like a multi-level thing you've got to imagine and hold in your brain at once here. That's why it's a little bit harder. Okay, so here's the dot plot for what? The height variable. This is the dot plot for the height variable. There were 5 basketball players, and then we're doing a dot plot of their height. So this is the value of, this is showing the distribution of x. Heights, right? Distribution of x, heights. Okay, so now here is the dot plot for the sampling distribution, samples of size 2. So what do? We took all possible samples from the 5 players, and we found the mean for each one of those. Here are those means. So there was 10, right? There were 10 samples of size 2. Here are the means. So what's the variable now? X bar is the variable. X bar is the variable. So you see there's two distributions at work here. There's the variable x, that's the original data set. And now we've taken all these samples and we've got means for each sample, and that's a new distribution, right? Our new variable is x bar. So I think this slide is pretty helpful.
I have a question.
Yeah.
Does mu stay the same all the time?
Okay, so here's the question. So if we have mu as our population mean, right? Our population mean for x. So the question is, what do we expect the mean of all the sample means to be, right? So now we've got all these sample means. If the population mean is mu, in this case 80 inches tall, then what do we expect for the mean of the sample means? So do we expect it to be the same as the mean of the original data set? It would make sense, right? Because we're taking all the samples and taking their means. Well, the mean of those means should be the same as the population mean. Okay, and here's the notation for that, right? So it's the mean when our variable is x bar. So this is the mean of the sampling distribution of sampling means, right? It's a mouthful. This is the mean of the sampling distribution of sample means. In shorthand, it's the mean of the means, right? It's the mean of the means. And the mean of the means is going to be the same as the mean of the original variable. The mean of the means will be the same as the mean of the original variable. And that's what we just said. So for the sample size of n, the mean of the variable equals the mean of the variable under consideration. In other words, the mean of the means is equal to the mean of the original population. So what about the standard deviation of the sampling distribution of means. What about the standard deviation of the sampling distribution of means? What will happen to this when the sample size increases? So you think you're going to take larger and larger samples. What will happen to the standard deviation of those means when you have a bigger sample size? Anyone give that? What's that? Bigger. So if you take more values in your sample, then does that distribution of means spread out more? Does that make sense? Randy? Okay, so I have some slides that show it. But so can you say more?
You went back a slide. So the sampling distribution mean or standard deviation is going to be less, right? Than the original standard deviation.
Okay. So let's just look at this. So here's the 5. Notice how spread out they are. And then we took means for samples of size 2. So did it become more spread out or less spread out? See, that's a little bit less spread out, right? So now if we took samples of size 4, would those samples of size 4 tend to congregate more around 80 or spread out more if you took samples of size 4? Do you see that the bigger your sample is, the more the mean is going to tend towards the mean. So the bigger your sample is, the more your mean of the sample will hover around the actual mean. So with a bigger sample size, we're actually expecting to see less spread of sample means. But I've got some good slides that show that. Okay, so here was the n equals 1. So the original data set. And then there's our the means of samples of size 2. Here's means of samples of size 3. Here's means of samples of size 4. And there's only one sample of size 5, and what does its mean? That's just the 80, right? So there's the one sample of all 5 of them, and its mean is 80. So this should make sense, that as you take larger and larger samples, the mean of those samples will be closer to the population mean. And this picture tells the story well. Because the bigger your sample you take, the more you're going to get. You're not going to get a chance of a pair of outliers, right? So if you had two in the sample, then you could get a pair of outliers. Like you could get the 2 lowest or the 2 highest. But the bigger your sample size is, the more you're going to get maybe an even distribution from your original set, meaning that the mean then will fall more toward the middle. Okay, so here's how we get this is the standard deviation of the sampling distribution of means. So it's the standard deviation of sample means. We're going to take the population standard deviation. We're going to divide by the square root of n. So what happens? The bigger that n is, the smaller that this is, right? If you divide by a larger number, you get a smaller number.
In a previous exercise, they said the lowercase n was comparable to n minus 1. In this instance, is the lowercase n the same? Because remember the capital N was...
Yeah, that was calculating the standard deviation. We actually haven't really talked about that yet, the n and n minus 1 thing. We're going to talk about that soon. Yeah, so just that's an important...
The total number then.
Just n. Just n, yeah. Okay, so let's look at an example here. So a report by the U.S. Census Bureau said the mean living space for single-family detached homes was 742 square feet. And they're saying assume a standard deviation of 568 square feet. Okay, so this is our mu. Mu is 1742. And the population standard deviation 568. Okay, and so it says if we took samples of 25 homes at a time. So we're going to take a sample of 25 homes and we're going to find the average square feet. And then we're going to take a sample of another 25 homes and find that average square feet. And we keep taking samples of size 25 and getting those means. Then we're going to have a bunch of these, right? We're going to have, x bar 1 equals, and then x bar 2. For every sample of 25 that we take, we're going to get a different sample mean. That's going to form a new variable. That's our new variable. The mean of these samples is a new variable for which we have a distribution. That's what we're talking about. So maybe this first one was, the first was 1607. I'm just making these numbers up. And then 1822. And then 1735. And then 1798. I'm just making those up out of the blue, just so we get a feel for. 25 homes, we're going to get a mean square foot. And we keep doing this. So now we're asking about the distribution of these means. The distribution of these means. What is the mean of the means? What's the mean of the sample means? What would it be? 1742. If we took all samples of size 25 and found the mean of those, we'd have the exact same mean as the population mean. And then what about the standard deviation of sample means? So that depends on your sample size, right? So it's going to be, for sample size of 25, it's going to be 568 over 5, divided by 5. Thank you. So with bigger sample size, we expect the means then to be crowding in around the actual mean. And so then that's a smaller standard deviation of the sample means. And the bigger your samples, the more that those sample means will be close to the actual mean. So smaller standard deviation. So this describes the sampling distribution for samples of size 25. So now we can ask a question like, so part C. What percentage of samples of size 25 have a mean less than 1,700 square feet? What percentage of samples of size 25 have a mean less than 1,700 square feet? We know how to do that. How do we do that?
Find standard deviation. So the area to the left of 1700 that you find, or whatever the standard deviation.
Yeah, so what are we going to find? We've got a mean and a standard deviation of a distribution, and I'm asking what percentage of samples of size 25, that's what our distribution is about, have a mean less than 1,700 square feet. What will we do first? Find the z-score. So what's the z-score? The z is going to be 1,700 minus, there we go. So because our sampling distribution is a normally distributed variable, we can use a z-score. So we can get a z-score for 1,700 square feet for samples of size 25 using its standard deviation. And what? Anyone got it? Negative?
-0.369 or 0.37.
So the z-score is negative 0.37. Anyone got a table handy? So a z of negative 0.37 gives a, so what percentage of samples of size 25 have a mean less than 1,700 square feet? What percentage? 35.57%. So if you have a normal distribution of a variable, then the distribution of sampling means is normal. If you have a normal distribution, then the distribution of sampling means is normally distributed, and you can get a z-score for that. Okay, so I think we can easily do, in a minute here, we can do 7.47, A and B on your sheet, and we'll be done. So, birth weights of babies. Mean birth weight. So our variable is birth weight. The mean is 3369, standard deviation 581 grams. So now we want to talk about the sampling distribution for samples of size 200. So is this sampling distribution going to have a large standard deviation or a small, very small standard deviation? The sampling distribution. Samples of size 200. With samples of size 200, you're likely to get a mean very close to the population mean. So all those sampling means will be very close to the population mean. So standard deviation will be of the sampling distribution very small. Right? When you take samples of size 200, you're going to expect to get means very close to the population mean. That's a huge sample. 200 is a huge sample. So your mean, you're expecting those means to be very close to the actual population mean. So the sampling distribution of sample means will be all very close to that or have a very low standard deviation. Okay? So go for it. Do part B.